So here I'm considering one copper rod moving in a uniform magnetic field. I've tried to draw the rod such that the velocity is perpendicular to the B field. So you can imagine the velocity is going to the left and the B field vector is pointing down. As a result, we'd expect our positive charge, if they were free to move perpendicular in this direction. But in reality, because it's a copper rod, our electrons would move in the opposite direction, going A to B. But anyway, let's consider our force. This is our magnetic force due to the fact that we have motion in a magnetic field. And we can write that as Q V cross B. And we've used the right-hand rule to show that we've gone V cross B, so our force must be in the perpendicular direction. I'm going to treat Q as positive and unity for simplicity. So if you see Q, that just means +1 unless I indicate otherwise. And so the net force that would happen would be Q, our integral from the whole length of our rod, which I'm going to describe as length L, V cross B, dot dl. I'll try and tidy that up. Okay, and so there we have it. We would have a case where now we're down on our rod. This is B side, this is A side. We would have our magnetic field, and I'm going to draw it down into the page. So this is the feathers of our arrow, and then we've got our velocity pointing in this direction here. So what we have is a build-up of we would expect to have a build-up of negative charge on this side and a build-up of positive charge on this side. Remember, we wouldn't have a current technically, because we would only be going A to B, so we'd have charge separation. That charge separation would mean that we would see the fact that this is the direction, this is the direction of our magnetic field force, and we'd expect to see an electric field form that points positive to negative, and that would oppose it such that we'd be stabilized when FB net is equal and opposite electric field induced. Then we could say that the voltage drop between A and B is equal to minus B A E dot dl. Because we've chosen A to B in this way, dl must point in the direction this way, which is in the same direction as our electric field. Our electric field is equal to minus V cross B, VB, because they're perpendicular, but still keep this in. So then as a result we get VBL as our voltage drop. Pause here for a second and carry on once I've drawn some more stuff. Okay, now I am showing a drawn picture of a case where we've connected our copper rod to some thin wires. We're assuming this is a very long loop, and that on this side here is our B field pointing up, actually, I apologize. It was pointing down previously. And so what we have is our induced magnetic force that's driving our charge carriers around. We can view it as now we have a loop of current. And that current, and what we've done is assume that no matter how much velocity we go in the left hand side, the circuit is so long that on this side we can treat it as still outside the magnetic field. So in this case we don't have a build-up of charge, we have a current induced. We can then work out what the induced EMF is, electromotive force. We've got to do our integral around our loop. This defines our loop. So we could view it as A going around to B and then back to A. So that where it's a closed loop, we would have a contribution from our magnetic forces plus our electric field dot dl. Our electric field is equal to 0 in this case because there's no build-up of charge. So what we have is B dl, which only contributes in this region here. All else is equal to 0. So we end up with a case where we just have our VBL. Now we need to figure out what current is induced, and that's why we've drawn this resistor as the resistance due to the whole circuit. And what we can do is then go EMF is equal to IR. So our current induced is equal to VBL over R. Nice thing to know about this is in this description we can still invoke the electrostatic approx that we've had, which is E dot dl is equal to 0 and a closed loop. So now I'm going to draw the scenario and work it out both with the force equation and also with Faraday's law. I'll pause here to catch up. So let's consider the case where half of our connected rod, half of our circuit, which consists of two rods connected by thin wires, are halfway in the magnetic field. We would expect there to be a force on this side, so we'd expect our force, magnetic force to induce an EMF around our circuit, which we would view as a current that's going counterclockwise. And let's do the calculations in two ways. The first is we can go, well, there would be an induced force equals QV cross B, which results, as we've seen before, equal to VBL, induced electromotive force, and our induced current would equal VBL over R, and this would be a case where it's going A to D to C to B back to A, positive, so we can view that as a counterclockwise. Okay, now let's do it with Faraday's law. So with Faraday's law, what we can do is we can say here is our electromotive force. It's going to be related to the change in flux. And what we're going to do is choose ds to be parallel to B. And the reason for that is it defines which direction we are going to consider the positive direction to be around our loop. And it turns out our loop direction is positive when clockwise. Okay, so now we go EMF is equal to minus d over dt b dot ds, and we're going to assume a moment in time when we have x amount of current section between a to d inside, so then we can write this as minus d over dt, b, l, and x will be a function of time, and it allows us to do our derivative. And what we note is that our dx over dt will be positive. We'll be increasing the amount of flux. This blx over t will increase with time, so that's why we will have a case where when we do the derivative this will be positive, so we end up with minus vbl, and when we turn in our current will equal minus vbl over r. Remember, it's negative in the clockwise direction, so that means we are traveling in the counterclockwise direction as we anticipated from the other description. So the key element is to consider the fact that our x, the region we're integrating, is going to be increasing with time, such that dx over dt will be greater than 0. I'm now going to draw another scenario, so I'll just pause here for a second. So let's consider the case now when our rod is completely inside. So this is our B, A, C, and D as before. We've already solved the case when we considered it in this direction. So force B would be in this direction. And by symmetry, it's got the same B field direction on C to D and the velocity, so I would expect FB to be this way. So what we can write is our net force due to our magnetic field will be such that we have F will be equal to the force B to A and we have the force C to D, so it would be D to C. That would equal 0 because of the symmetry of the situation. So when we try and find out the EMF, we would get F net P plus E. Well, we know the E is equal to 0 dot dl, and the result of this would be equal to 0, so we'd have no current. The same can be true if we consider Faraday's law. So here we have our derivative of our, that should be closed, time derivative of our flux, P dot ds. We've chosen ds to be positive when our current, with our B field pointing into the page, and so our ds would be pointing in the same direction. So again, we consider EMF to be greater than 0, i.e. positive for the count. Clockwise direction as before. And so what we can do is we end up with a case where we consider minus d over dt, the full area encapsulated by a surface, which would be bl squared. That has no time dependence, and so we end up with 0, so we have no current again. Then the next thing we're going to do is complete it by having the circuit completely out of our B field on the left hand side. So I'm just going to pause once more. So here I've just quickly drawn our scenario where only the side C and D, this part, is in the B field. I've drawn the well-known vector directions that we've had, and then we could just simply find that we'd expect, in this case, FB equal QVB, and that means our induced, if we assume again that Q is unity and positive, we got BBL. In this case it will go C to D, A to B. This is clockwise, so this will be a clockwise solution. So let's look at our Faraday's law. So we have EMF is equal to minus d over dt. B dot ds, we keep the same convention that we've been using, and so we write as d over dt BL x, and x will be a function of, because the amount of surface will change because of the velocity. Now in this case we have the scenario that this will shrink as we move our velocity. As our velocity moves in this direction, this dx will shrink. So x over as a function of t is such that if we take the time derivative, it'll be less than 0. So we end up with a case where we have a positive BLV. And remember that we had defined our surface such that DAS is parallel to B, such that our EMF is positive in the when this is positive, that corresponds to a clockwise direction. So we end up with the same result in the two modes. Now, why have I laboured this? Well, there's a very important element. One way of writing this, if we considered everything in terms of our V cross B contribution, there is we can describe the scenario when our frame of reference is not the loop itself. If we consider the case when we have it, so then this is our loop, and we imagine that we are an observer on the loop, then the velocity of the loop is equal to 0 for our frame of reference. And then what we'd imagine seeing is a B field which cuts across as a function of time across this, such that we begin with we start seeing a current that's induced in the counterclockwise direction. Then it disappears when all the magnetic field is in there, and then when the magnetic field leaves, current is induced in the opposite direction that eventually disappears too. So in the Faraday's description, we were able to describe that in each case. So what we could do is consider the first case where we're partially moving in. Our velocity is equal to 0, as I said, so we would expect our current to equal 0 if we just use the F equals V cross B. But fortunately in the Faraday's law, we can just view everything in terms of a change of dB over dt. Now bear in mind, we have assumed that it's a constant magnetic field that we're going into, but because of the frame of reference of us being on the loop, we can imagine that our magnetic field is changing, and it's changing in such a way that in this scenario is growing. So this would be a positive term. So we could write this as is growing in the case where it would increase with x. So then we have the same algebra. We have d over dt and have flux integral would be BL x of t, which ends up being minus BLV. Remember, dx over dt will be positive because it's growing, so we keep our negative sign. So our current will equal BLV over the resistance of the wire in the counterclockwise direction, which is what we said originally. If you do the case when we are fully in is a non-trivial one, because we would view this is a case when we're completely inside the magnetic field, then there's no change in the magnetic field flux in the region we're considering. So then d over dt, our flux, is equal to 0. I just want to clarify something up here where I've made a typo. What I've done is said that dB over dt is growing in this case. That's because it appears to this person that the magnetic field is encroaching across this surface, when in fact the real important aspect is the fact that we have a change in time of our magnetic flux. Second case. So what we could do is view this scenario for that frame of reference. B is equal to a constant. Does not change. When we have the scenario where the other side has left that uniform magnetic field, we still have V equals 0, so we would not be able to describe the results in terms of F equals QVB as we've done before. And so what we have is EMF d over dt BL. This is our region magnetic flux. We are taking flux away because the loop is leaving the magnetic field, and so that means that our derivative of x with time is negative, so we end up with a positive BLV. So our induced current is going to be BLV over R, and in this case now it's a positive sign because it's clockwise, whereas previously it was negative and counterclockwise. Now, why is this interesting? Well, our EMF is equal to, as we described before, F, we could consider a magnetic force plus an electric field. We were happily describing the situation in all frames of reference apart from that on the loop, in terms of an induced EF V cross B force that was inducing an EMF and a current. But that's not true. We could view it as a more general scenario that there is an electric field, and that electric field is non-conservative, and that our EMF, this electric field, is a full electric field which does vary on time, such that I'm just going to clarify. We mean that if we have a time dependent electric field, then it's not conservative. And so what we're essentially doing is the change of the magnetic field with time is actually into a real electric field, which is non-conservative.